The following video is on limits that go to infinity. Remember that there are three ways that a limit can fail to exist. The first is if the limit from above and the limit from below disagree. The second is if the function is oscillating wildly and we're unable to determine what y value the function is approaching. The third is if the limit as x goes to a from either above or below goes to either positive or negative infinity. This is the case that we're going to focus on in this video. Recall that if we have a fraction, we can think about it as eating slices of pizza. If I get 1 over x of the pizza, that means that I get to eat 1 out of x equally sized slices. So if I slice my pizza up into a certain number of slices, and I go backwards and start removing slices, notice that the amount of pizza that I get to eat is getting larger and larger. In other words, as x gets smaller, 1 over x gets bigger. Another way to see this is to draw a chart. So if x is equal to 1, then 1 over x is 1. If x is equal to 2, then 1 over x, if x is equal to 1/2, then 1 over x is equal to 2. If x is equal to 1/3, then 1 over x is equal to 3. If x equals 1 over 100, then 1 over x is 100. If x equals 1 over 1,000,000, then 1 over x equals 1,000,000. So the limit as x goes to 0 from above of 1 over x is infinity. Now technically the limit as x goes to 0 from above of 1 over x does not exist, but writing that this limit goes to infinity is more informative than just writing dne. What about if we wanted to approach 0 from below? We could draw the same chart that we did before and plug in values of x that are getting closer and closer to 0 from below. So values such as -1 over 1,000,000. When I plug that into the function 1 over x, I end up with -1,000,000. So again, we see that the limit as x goes to 0 from below of 1 over x, in this case, is negative infinity. Again, this limit does not exist, but it's more informative for us to write that it goes to negative infinity than to just write dne. Another way to look at this is by looking at the graph of the function. We see that as x gets closer and closer to 0 from above, the y value is getting bigger and bigger. In other words, it's going to infinity. And as x gets closer and closer to 0 from below, the y value is going to negative infinity. In fact, this pattern continues. For example, if I have the function 25 over x plus 1, as x gets closer and closer to -1, the denominator is getting closer and closer to 0, but the numerator is not 0. So notice that if we approach -1 from below, I end up with 25 in the numerator and a very tiny negative number in the denominator. My notation for this is -0. Anytime I have 25 over a negative tiny number, that goes to negative infinity. Similarly, if we approach -1 from above, I have 25 over a very tiny positive number. Again, my notation for this is +0. Anytime we have 25 over a very tiny positive number, the value goes to positive infinity. any finite non-zero number divided by a value that's going to 0 from either above or below will go to plus or minus infinity. Consider the limit as x goes to 3 from above of x minus 2 over x minus 3. Notice that the numerator is going to 1 because if I do direct substitution, I'll have 3 minus 2. The denominator, on the other hand, is a very tiny positive number. So 1 over a very tiny positive number goes to infinity. Another example, if x goes to 1 from below of x squared plus 5 over x minus 1 times x plus 2, I end up with 6 over a very tiny negative number, which goes to negative infinity. If I take the limit as x goes to 2 from below of 1 over x minus 2 quantity squared, I get 1 over a very tiny negative number squared, which makes it a very tiny positive number. So the whole thing goes to infinity. And finally, if I have the limit as x goes to 0 from above of x minus 2 times x minus 2 over x times x minus 3, I have negative 2 over a tiny positive number times negative 3. So that's the same as negative 2 times a negative tiny positive number. So the whole thing goes to positive infinity because the negative signs cancel out. There's one warning, however, when doing these problems. If the numerator and the denominator are both going to 0, then we have an indeterminate form. We know that if we have an indeterminate form, we must use another limit technique to solve the problem. For example, let's look at the limit as x goes to 2 from below of x minus 2 times x minus 3 over x minus 2. In this case, we get 0 over 0 when we do direct substitution. This is not good. This is an indeterminate form, so we must use another technique. Luckily, we learned that we can cancel the x minus 2's out of the top and the bottom, and we end up with the limit as x goes to 2 from below of x minus 3, which we can use direct substitution to get negative 1. That's much better.